So let's wait until everyone's settled. So hi, my name is Ümit Seren. I'm an HPC system engineer at the Vienna BioCenter, which is also home of 4 life science institutes in Vienna. And I want to tell you the story about our journey of implementing a 200-node Slurm cluster on top of OpenStack. But before I start, maybe just a show of hands, who here in the audience has experience with OpenStack? That's some people. And who is currently running an OpenStack installation? That's actually the same amount of people. Great. Good. Let's get started. Anyone remembers the great talk by Damien Francois from last year's FOSDEM about the Cloudster? So if you weren't at the talk, basically the Cloudster is a hypothetical system of heterogeneous hardware that not only allows you for traditional HPC workloads, but also new emerging workloads around big data and stateful applications. And when we started the OpenStack project, this was something that we had in mind. A system that would not only allow traditional HPC workloads, but also these new use cases. So meet the Cloud Infrastructure Project, or short CLIP, that was started to realize this idea. The goal was not only to consolidate the various compute clusters we had on campus and replace it with a new HPC system, but realize the vision of a software-defined data center strategy that would allow a system such as Cloudster. We chose OpenStack as a cloud framework, and a team of 4 full-time engineers was formed and tasked to deliver the project in multiple phases. And we set 3 big milestones for the project. Initially, we wanted to basically deploy a traditional batch scheduling system based on Slurm on top of OpenStack. Once this was finished, we would implement new interactive applications such as RStudio, Jupyter Hub, and others. And then finally, we would extend the use of OpenStack to all kinds of long-running stateful applications such as databases and web applications. So this is how it's supposed to look like. You have basically on the bottom a set of heterogeneous hardware, and on top of that, we have the OpenStack private cloud with which we can provision different flavored VMs. And on those VMs, we can then provide different services ranging all the way from a traditional batch scheduling system to a Spark cluster, Jupyter Hub, RStudio, and other things. Let's also briefly talk about the CLIP architecture and hardware. The CLIP pool of hardware consists of around 200 compute nodes that are split in 4 different types. Type 1 compute nodes are split into subcategories. 20% of those are high frequency, low core count Skylakes, and the remaining 80% are high core, low frequency, again, Skylakes. Type 2 are large memory nodes. We have 1 4 terabyte machine and 3 1.5 terabyte machines. We have 12 I/O nodes with NVMe flash storage for around 250 terabytes of BGFS scratch storage. And we have 6 GPU nodes with a mix of V100 and T100. All of those nodes are connected to an existing Cisco software-defined fabric with 100G Ethernet. And also there is existing data center infrastructure such as network attached storage of around 10 petabytes. So as I mentioned before, the plan was to deliver the project in multiple phases. And the project started at the end of 2017 with a proof of concept to better understand OpenStack. This was on a really small scale, 3 controllers, 1 undercloud, and 2 refurbished hypervisors. And this took us around 2 months. This was then followed by a deep analysis of OpenStack with specific regard to the impact on HPC. So we were looking at different deployment methods, the tooling around it. We also developed tighter integrations with existing data center infrastructure such as storage and DNS. And also we did some benchmarking. This was supposed to take 8 months. In the end, it took us about a year. At the end of 2018, the procured hardware arrived and was installed. The goal was to have a production deployment of the cloud and a payload on top of this within 4 months. This actually took us in July 2019. Our Slurm cluster went into production. And since then, we are working on delivering the second milestone, the interactive applications. And if you want to know more about this, and if you attend the FOSDEM, my colleague Erich Birngruber will talk about this in the HPC track. So now let's talk a bit about our experience with OpenStack for accomplishing the first deliverable, an HPC system. And I want to first discuss how we deploy the cloud and how we operate it, and our experience regarding those 2 points. There are a lot of OpenStack installers out there. So every major OpenStack distributor has its own installer. We decided to go with Red Hat OpenStack because of 2 reasons. We have an existing support contract with Red Hat, so we can create support tickets. And we also wanted to have a tight integration with the Cisco software-defined network, and Cisco only provides installers for Canonical and Red Hat. And Red Hat OpenStack uses Tripleo, a system called Tripleo, which stands for OpenStack on OpenStack, to deploy the cloud. So how does Tripleo work? Tripleo consists of 2 parts. There's a so-called undercloud, which is a single node installation of OpenStack. You can see it here with some of the services. And the most important service is probably Ironic, which is used to provision bare metal machine that we'll need actually to deploy the overcloud. And then using this undercloud, we then deploy the overcloud. This is the actual cloud that will run our production payload. And there are a couple of benefits to this approach, but the biggest for us was that you as a sysadmin only have to learn one set of APIs. So for example, we use the image service Glance in the undercloud to store the operating system images for the hypervisors, compute nodes, and the controllers in the overcloud. And we use this also the Glance image service in the overcloud with the same set of APIs to store the VM images for our Slurm payload. So that makes it easier for us to operate the cloud. There are 2 ways how you can install the cloud in Tripleo. You can use the web UI, or you can do it from CLI using YAML files. And because we were new to Tripleo, we had a look at the web UI. It looks pretty nice. You can customize your clouds, set configuration regarding network and storage, and then just deploy it. But the problem is we realized that this is not the approach we can take, because we didn't only have one environment. We decided to have 3 OpenStack environments with almost basically the identical hardware that are slightly different, just to test upgrades on different configurations. So basically clicking 3 times through the web UI is not scalable and doesn't allow for fast iterations, and also it's not reproducible. So we decided to scrap the web UI and just do everything from the CLI. One important thing is that Tripleo internally uses a lot of OpenStack services such as Ironic or the Glance image service to deploy the overcloud. But it does not only use Heat, and it also uses one important service it uses is Heat, the orchestration engine of OpenStack. Heat will provision you the bare metal machines in the overcloud, and then on the bare metal machines there will be a Puppet running, which in turn runs an Ansible. Yes, you heard right. This sounds very convoluted, and it's also very complex, but there's work to simplify this. We ourselves also had to decide to use a config management tool because we needed to configure data center resources like storage, network. That's not done by Tripleo itself. And we decided to go with Ansible because that was the easiest for us to use. And our deployment basically is done in 3 steps. Basically, we have a set of Ansible playbooks that live on a special Bastion VM that are used to install or deploy the undercloud, the bare metal machine, and install the Tripleo software. And we have to do it actually for 3 environments. So this VM will provision the undercloud for the 3 environments. Once the undercloud is deployed, we have another set of playbooks, Ansible playbooks, that will do some validations and then feed some customized YAML files into the Tripleo installer to actually deploy the overcloud, and then do some post-validation. And finally, we have another set of playbooks that will do post-deployment configurations. For example, upload some VM images for the Slurm payloads that we need later, or pre-create some network constructs. And we use the same Ansible playbooks to scale up and down the overcloud or to reconfigure the overcloud. Another important thing is that all the code for the YAML files and the Ansible playbooks, they live in 2 Git repositories. So we do some kind of GitOps, basically. So this works actually fine. However, there's some challenges that you should be aware of. Tripleo, the system is pretty slow because it runs Heat, that in turn runs Puppet, that also runs an Ansible. So for example, if you need to change one configuration of a service and you want to restart the service, you would have to run a so-called stack update that will run Puppet on all the nodes. And this will take on our production system 60 minutes. As you can imagine, this is pretty painful, especially in the beginning when you haven't really set on a final configuration of your cloud. And so we thought, okay, let's just use Tripleo to get a running cloud and then use Ansible to customize it because that was much faster. However, we quickly realized this is also not a good solution because once you do a stack update, and you need to do a stack update if you scale up or down the cloud, Puppet will override all your Ansible modifications, and then services will be down, which is not acceptable. So we decided to compromise. Let's basically, in the beginning, when we haven't settled on a final configuration, use Ansible to try out different settings, and once we settled on the final configuration, we would take those configurations back into the Tripleo framework and use the Tripleo exposed configuration stances. For everything else, we continue to use Ansible. So for example, we needed to set up the, we have an Ansible playbook to talk to this Cisco software-defined network controller to pre-provision the networks for the free environments. And the nice benefit is that we also have a playbook that can move a node from one environment to another and back. So let's change gears a bit and talk also a bit about operations. As I mentioned before, we have these free OpenStack environments that allow us to try out different configurations on new software packages. And we have all the code or the configuration of the cloud in Git. So this is very reproducible. But what about software packages? Red Hat releases on a regular basis updates to base OS packages and also to the OpenStack packages. How can we make sure that we have reproducibility regarding software? We thought long about it and then decided to use Satellite. It's a Red Hat product. The upstream open source product is called Foreman, where we basically create free software lifecycle environments that correspond to our OpenStack environments. And then we create content views. These are basically sets of RPM repositories. And these content views we can version, so we can freeze the versions of those RPMs. And we can promote them in those free lifecycle environments. That means we can test, for example, up newer OpenStack packages in the dev environment. And if they work out, we can promote them to staging or eventually to production. As any other software, OpenStack also has its fair share of bugs. And for some of them, we came up with some workarounds. For some of them, we opened tickets with Red Hat, and some were already fixed in a future version of OpenStack or of its services or packages. And to keep track of all of this, we created a JIRA board. We call it Clip Release Engineering. And when we encounter a bug, we triage it, we document it. We come up maybe with a workaround, or we create a ticket. But most importantly, we track it in this JIRA board. And then when we upgrade the OpenStack or some of the packages, we can come back to this board and have a look and see which workarounds we have to unroll because the bug was fixed in the version that we deployed. So some concluding remarks about the deployment and operations of OpenStack. So OpenStack and Tripleo are pretty complex. So this is the take-home message you should take from this talk. You need a dev environment and maybe also a staging environment to test upgrades. And also having package management is pretty crucial. Upgrades can break your cloud in unexpected ways. So our biggest pain point was going from a non-containerized control plane to a containerized one. And also sometimes you need to customize those upstream containers you get. So having a container build pipeline in Jenkins, for example, is super helpful for that. Tripleo is also a very well supported out-of-the-box installer for common cloud configurations. If you want to do something very exotic, then the rigid framework is a bit challenging doing this part of in this rigid framework. I didn't talk about the next one, but obviously continuous integration, regression testing, monitoring is crucial. And finally, Infra as code, or GitOps, how they call it nowadays, is the way to go, but it requires development discipline. So you need to do proper PRs, you need to do release management, and that has to be done. So now that we have the cloud, our cloud, how do we deploy our HPC payload on top of that? We do this in a two-step process. So we use the heat orchestration engine in the overcloud to provision the VMs that will later run the Slurm cluster. And we also generate an Ansible inventory. This is the first step. And then in the next step, we use an Ansible playbook to install and configure our Slurm cluster. And we use either self-developed Ansible roles, but also we rely heavily on Stack HPC's public Ansible roles. And then we can use the same playbooks to scale up and down our Slurm cluster or actually reconfigure it. What we also do is we register the VMs with satellite, so we can now manage the package versions, for example, for Slurm or for the open HPC packages or for any other software packages that we need. And because we have a staging environment, we can test both different configurations of our Slurm cluster plus different versions in those environments. And if they work out, we can just roll them over to production. And this whole approach can also be used not only for a Slurm cluster, you can use it for other complex systems, Spark cluster, K8s cluster, BGFS cluster. And we do use them also, this approach for those workloads. So maybe one or two slides about benchmarks, because we are running, or we deploy a virtualized Slurm cluster. And you might ask yourself, do we get bare metal performance? And in order to get really good performance, you need to apply some tunings. And this is a non-exhaustive table of the tunings that we applied. The important thing is that every tuning comes with its own downside or caveat. For example, with NUMA clean instances, you will lose the ability to do live migrations, and also you cannot mix different VM flavors on the same hypervisor or compute node. This is not a big issue for our Slurm cluster, but you have to be aware of that. We also use static huge pages. If you use that, make sure that you leave enough memory on the host system, otherwise you cannot do any stack update, because as you remember, Heat will run Puppet on the nodes, and the OOM on the host will kill your Puppet process, and basically your stack is in a failed state. ISIL CPUs also improves performance, but this will force you to use SRV for good network performance. And finally, for GPUs, you need an NVMe flash drives, you need PCI pass-through, and for getting really good network performance, you need to use SRV. But keep in mind that those tunings, they have a smaller feature set compared to their fully virtualized counterparts. And with all these tunings, we can basically achieve almost bare metal performance. And I don't want to bore you with plenty of charts. I want to show you one chart, which is maybe interesting. Here you can see different bioinfo workloads running in parallel on a host. So and you can see the standard deviation of execution time, so the jitter. And you can see if I run the bioinfo workloads in parallel on a bare metal machine without isolation, you get a lot of deviation, so almost up to 10% for one of the workloads. If you split the compute node along the NUMA boundaries and spin up two VMs and run the workloads in those VMs, obviously they are isolated from each other, and you can reduce the jitter quite a bit. To be fair, Slurm on a bare metal machine using C groups does an equally good job. So maybe some issues and pitfalls that we encountered when we deployed our HPC payload on top of OpenStack. So this is not only OpenStack related, but still. So Ansible is slow. For example, if we run our Slurm playbook end-to-end second time, that means no modification on our production system, this takes an hour. So if you have some recurrent operations like mounting new volumes or changing the causes, make sure you tag them with Ansible tags so you can run them if you just want to run those tasks. Also, using fat images can help to cut down on installation time that we didn't use. Satellite is also pretty good to control the software versions, but remember to remove the upstream CentOS images if you deploy the VM, because otherwise all the versioning is for nothing also happened to us. Some issues you will also only hit under scale. So, we tested the deployment on a small scale, on the dev environment, everything worked out. And then we went to provision our production system. We ran into a nasty Cisco software-defined networking bug that after 70 nodes, we had to scale up in batches, otherwise it would fail. So be aware of those issues. And having like environments that isolate or are isolated from each other, that works pretty well. But remember that this stops basically at shared infra components. So what do I mean with this? So once we did the deployment of our OpenStack on the dev environment, we triggered some kind of race condition that caused an outage in the whole data center, also for our users and also production workloads. And this is specifically true if you tightly integrate OpenStack with existing data center infrastructure. And then finally, also be aware of unintended consequences of code changes. So we once wanted to scale up our Slurm cluster, but we accidentally triggered a redeploy because months ago we had a one-line change in the heat configuration, and heat has sometimes will sometimes reprovision your VMs if you change something. And so basically our maintenance window was much smaller, but then ended up to take the whole day because we redeployed everything and then we ran into the scaling issue. So, this you should also keep in mind. So to summarize everything, basically the entire talk, and show you the bad, ugly, and good parts, OpenStack is incredibly complex. And unlike, for example, VMware, it's not a product, it's actually a framework. So you need really a couple of, at least a dev environment to test upgrades, different versions, and to understand them also better. And then scaling, as I showed you before, above a certain amount of nodes will be an issue. So I would not use OpenStack to maybe deploy 1,000 nodes unless you have a very good understanding of OpenStack and also enough engineers to debug issues. And cloud networking is really hard, especially in our case when we deeply integrated with our Cisco software-defined network. So these are the bad parts. On the good side, it's an open source software with vendor support. So that's not bad. It integrates pretty well with data center infrastructure. And it has an API, so you can really use it to implement the vision of a software-defined data center. And as I showed you, you can easily deploy different payloads next to each other. And you can deploy virtualized or a bare metal HPC cluster. You can deploy container orchestration engines or whatever you might need, actually. So with this, I want to finish the talk, and this is basically our team that implemented the project, and I will answer any questions you might have.
When you were looking at optimizations, did you try things like DPDK for speeding up the network, or did you just do the SRIOV instead?
We didn't really specifically look into DPDK, but we decided relatively in the beginning to use SRIOV because we knew that it will give us the best performance. I mean, there are other approaches, like there's ASAP Square, so we have Mellanox NICs, and they support so-called OVS offloading. So you can have those OVS rules that basically define how it's switched. That's usually fully virtualized, and you cannot really achieve good performance. You can offload them into the smart NICs, basically, but they also use SRIOV under the hood. So in the end, for simplicity, we just decided to go with SRIOV.
Anyone else? Okay, if not, thanks very much.